everyone. This week we are going to be talking about triangles, starting with triangle edges and area. So, our first question, the length of the base of a particular triangle, is 2 centimeters more than its height. If the triangle has area 12 centimeters squared, what is its height? Okay, well, as a reminder, here is the area formula for a triangle. It is half of that of a square, or any rectangle actually. So if you have a rectangle like this, the area of this rectangle we know is base times height, where this is height and this is base. Where this is height and this is base, right? So this is the area of a rectangle. Now if we want to find the area of a triangle, we kind of just split that in half. So we divide this in two. We only want this portion here. So that would be base times height divided by 2. As it turns out, this formula here works for any triangle, not just, right triangles. It also works for triangles that look like this. As long as you know the height here and you know the base here, base, height, you can still apply this formula to find the area. Well, and that was, a brief crash course. But on to our actual problem. So we know a few points. We still have this formula here, base times height divided by 2. We know that the area is 12. We also know the relationship between the height and the base. The length of base of this triangle is 2 centimeters more than the height. So base is equal to height plus 2. And we can substitute that into this equation, and we'll get height plus 2 times the height divided by 2 is equal to 12. And then we can multiply both sides by 2 to get 24. 24. Now at this point, if you don't know if you don't know the quadratic formula, or you don't know how to solve quadratic equations, this is the point where you kind of have to guess a check. For those of you guys who do know the how to solve quadratic equations, you get something like h squared plus 2h minus 24 is equal to 0. And you can simplify that into h plus 8 我把3以3把嘢4 6嘢4 So you'll get something that looks like this. You'll find that if you actually distribute this out, it'll equal to this. These two are equivalent statements here, except this is a more helpful format because we can figure out what h is in this case. So h is equal to -6 or 4. And, well, it can't be a negative number, unfortunately. So we can conclude that the triangle's height is 4 cm, and that's it. That was kind of a mess, but height can't be negative. Alright, on to our next equation. In how many ways can we form a non-degenerate triangle by choosing 3 distinct numbers from the set 1, 2, 3, 4, and 5 as sides? Okay, well, think about triangles, this is kind of what a degenerate triangle looks like, and you'll find that it's not actually a triangle at all. And a degenerate triangle would look something like this. This is a degenerate triangle, or like this. This is also a degenerate triangle. My point being, in a triangle, you have 3 sides. We'll call this A, B, and C. And the sum of A and B has to exceed C. So A plus B must be greater than C. And the reason for that is that if C was greater than A plus B, you would have a triangle that looks like this. So A plus B, this is A, this is B, and C would be even greater than both of them. It look like this. You can't actually form a triangle like this. This is a degenerate triangle. And what we want is a perfectly normal, non-degenerate triangle. And actually, similarly, we have a triangle like A, B, and C again. A, B, and C. If you let's assume that without loss of generality, A is greater than B, right? Well, A minus B A minus B, you look like this, A minus B has to be less than C, I believe. So the difference between A and B, let's say you have a long line like A, then you have a long line like B. If this was not true, if A minus B is greater than C, you have A here, and then you'll have B here, and you'll have this difference between them, right? But because it's greater than C, C would be like kind of like right here, but it won't ever make the gap. And you can try like whoosh. Oh. It won't ever make this gap between here. Like it can be like the angle here can be infinitely small, and yet C still won't connect these 2 points enough so that it actually forms a degenerate triangle. I mean, a non-degenerate triangle. Gosh, I'm mixing up my terms. Anyways, these are kind of our requirements here, assuming that A is greater than B. And it works for all the sides actually, so it's not just particular A and B. You can actually say the same, so B plus C has to be greater than A, and C plus A has to be greater than B, and A plus B has to be greater than C. Okay, well, this is relevant to our conversation because we have the set 1, 2, 3, 4, and 5 as sides. Because we have that requirement as stated below, we know that we have to choose 3 numbers, so the sum of any of the 2 exceeds the third. And so out of our possible side lengths, it cannot be 1. And the reason for that is because 1 plus 2 would not be greater than 3. 1 plus 4 would not be greater than 5. And you can choose any set with 1 here, and it wouldn't form a non-degenerate triangle. You can test all of them out if you wish, but I will move on. We can also choose 2 as our side length, so we crossed out 1, let's move on to 2. If we have 2, and this is kind of just counting, we don't actually have, there's a strategy to solving these problems. We're not just gonna try to figure out willy-nilly, but this you will have to test a few points. And so we know that with 2, the other possible pairs for the other sides are 2, 3, 4, and 2, 4, 5. And you can test if this is true too. So we've knocked out 2 here, and so we are left with 3, 4, and 5. And it turns out we can use 3, 4, and 5 as our pairing too for our side lengths for a non-degenerate triangle. So we are left with 3 options. There are 3 ways that we can choose distinct numbers from the given set to form a non-degenerate triangle. Main point is, you should remember that rule here, A, B, C. A plus B must be greater than C. Okay, I will see you in the next video where we will talk about the angle bisector theorem.